Hello everybody. We use blue waters for large-scale first principle modeling of nuclear structure. And here is the list of people who are involved in this project. We have a number of graduate students and postdoc who utilize blue water resources for their research, as well as computer science collaborators from the Czech Technical University who help us with code development. But first of all, why is this important? Why does it matter? Nuclei account for over 99% of mass of ordinary matter in the universe. What you see, what we observe in the sky, the stars, supernova, neutron stars, galaxies, it all is manifestation of nuclear effects that are driven by gravitational compression. Unfortunately, all these processes and nuclear excitation that normally occur in stellar environment, they are quite rare here down on Earth's surface. So we have to build powerful accelerators if we want to study them. An alternative approach is to utilize powerful supercomputers and study these systems numerically. And that's the name of the game that we play on blue waters. So atomic nuclei, as you all know, are made up of protons and neutrons, which themselves are composite particles made up of light quarks, then interact with strong force, which is one of the four fundamental forces of the nature. The nuclear force is a residual force, and hence it is quite complicated. In fact, its exact form is still unknown to some extent. However, what is known is that, for instance, nuclear interaction have 2, 3, and 4 body parts. So ab initio approaches to nuclear structure and reactions, you start with nuclear interaction that can come in many different forms. Then you solve many-body problem, and you obtain nuclear wave function, which is the complete information about a system that you study. And you can also compute nuclear properties. And in the last step, you use this wave function nuclear properties to compute nuclear reactions, compute reaction rates, and cross-section. So how we actually proceed? The approach that we choose is configuration interaction approach. You choose physically relevant model space and construct its basis. In nuclear physics, this basis is made up of eigenstates of many harmonic oscillators. It is because in such a basis, it's easy for us to exactly factorize intrinsic degrees of freedom from center of mass periodicities. In the second step, you compute your Hamiltonian matrix. I just depicted here the distribution of non-zero matrix elements in this matrix, and you can see that generally it is quite sparse. And in the final step, you use Lanzos algorithm to find the few lowest lying eigenstates and eigenvectors of the nuclear Hamiltonian. The eigenvalues correspond to energies which are observable, that can be measured, and your eigenvectors are then given as expansion in basis of your choice. And here is the key challenge of this configuration interaction approach, and it is the scale explosion in size of your matrix as you increase the number of total harmonic oscillator excitations that you allow in your basis. That can be related to the size of the box in which you are trying to describe your nuclei. And of course, heavier nuclei you have, the larger box you need, but at the same time, the dimension grows quite dramatically. This red line represents the biggest dimensions that we can handle on the biggest supercomputers currently in existence. It's around 10 billions, which is an impressive number. However, if you want to model medium mass nuclei, you can go at most up to nmax4 or nmax6, which is not enough to obtain converged values and to describe the long-range tail of the wave function, which is important for nuclear reactions and for observables that are sensitive to this tail. So the limits of applications of ab initio studies is mostly on lattice nuclei. And this is exactly the reason why we use blue waters, because we like the fact that it has a large aggregate memory and quite high peak memory bandwidth. And the approach that we are using in this configuration interaction approach is called symmetry-adapted. That means that we are using symmetries, exact as well as partial symmetries that are not perfect, but they are fairly good. And we use them to establish a basis which is very suitable for description of low energy nuclear dynamics. So here are the quantum labels of our basis states. So first this capital N, that's the number of harmonic oscillator excitations. Next one, we actually divide or factorize our basis into spatial and intrinsic spin part. So this piece is intrinsic spin part. We see that we know exactly what is the total spin of the protons, neutrons, coupled total spin. And in a spatial part of our basis states, we organize it according to SU3 group, which is the symmetry of harmonic oscillator, but at the same time, it is also related to intrinsic deformation of atomic nuclei. And next, the orbital angular momentum is also a good quantum numbers. So you can see that we designed this basis to be highly tuned for description of deformed system of nucleons that rotates. And I would like to say some words about the codes that we are using. We implemented everything from the scratch. The code is actually a mixture of C++ and Fortran subroutines. It's parallelized with MPI OpenMP approach. All our codes are publicly available. And what is interesting is that computational effort is absolutely dominated by construction of a Hamiltonian matrix. Only around 10% of the time is spent on solving the eigenvalue problem. And here is the way that we map MPI processes to Hamiltonian. But if you look at it, if you just start with this matrix, you would find that distribution of non-zero matrix elements is not uniform, and therefore you would end up with non-even computations, which is not well load balanced. So what we do, we use round-robin distribution of basis states among MPI processes, and in this ways, this matrix that looks, this is the structure of original matrix. If you use multiple processes, you see that now the blocks are fairly same. It looks very similar. They have the same number of non-zero matrix elements, and that leads to low balance computations. Our codes have also good scalability in terms of MPI processes and OpenMP threads. And this is one of the highlights of our results. This is the emergence of important configurations in nuclear wave functions. So this is the ground state of lithium-6. The different colors correspond to different spin components. But what you see that the wave function that I'm plotted here, which is the ground state of lithium-6, is absolutely dominated by just single color. That means that only one spin component is dominant. The other are almost negligible. And then this horizontal axis shows the formation. And you can see the highest peaks and the largest components of the wave functions are on this very edge of this graph, which corresponds to most deformed configuration. So you see that lithium-6, even though it's a light nuclei, it tends to get deformed from the get-go. And actually, when you see this, all these configurations contribute to almost nothing to low energy dynamics of nuclei, and therefore we have our partial symmetries allows us to implement very nice model space truncation, and that allows us to move to heavier nuclei, such as neon-20. So in this calculation, the complete space is 4 times 10 to 12. Our adapted space, which adapted space is just 10 million. The excitation energies compare quite well with experiment. And this is the results for neon-22, which is even heavier nuclei. And again, we have a good agreement with experiment. And I also plotted quadruple moment that shows just distribution of matter in nuclei. And this observable is sensitive to the tail of your wave function. And we can go even higher. So this is magnesium-28 rotational spectrum. Again, fairly well compares to experiment. Complete space is 513 billions. Using symmetries, we can truncate the space down to 23 millions. The number of blue water nodes that were used for this calculation is a little bit over 3,000. The size of Hamiltonian was 20 terabytes. And here is the performance on the blue water system. The basis construction, even though we have to iterate over 513 billion states and then select only a subset of them, this takes only 10 seconds. The matrix construction absolutely dominates the calculations, and the eigenvalue problem in this case represents 7% of the overall computing time. And here is the result for other nuclei, magnesium-29, fluorine-29. And here are Be2 transition strengths. These were recently measured in Triumph National Lab in Canada. And we are really happy to see that our results match quite well experiment, because the Be2 transition strengths are very sensitive to the tail of the wave function. So it's a long-range correlations that our wave function describes quite well. So we build basically a database of nuclear wave functions for different medium mass nuclei, which is also publicly available. And our students now using this database for further studies. So Ellie Dreyfus is calculating reaction rates. She's looking at alpha capture on oxygen-16. She uses the wave functions for neon-20 that were computed on blue waters, calculates spectroscopic amplitude. From spectroscopic amplitudes, she gets reaction rates, which can then be used as an input to study, to simulate X-ray burst nucleosynthesis. And this just shows how sensitive reaction rate of single reaction is on abundances of isotopes created in this cataclysmic event. Another student of ours, Robert Baker, who is actually going to defend his thesis next week, implemented a method that's called Lorentz integral transform method and coupled with our approach. And he's computing nuclear response functions, which are actually something that shows the response to external probe, such as photon, electron, or neutrino. He basically takes the wave function from the blue waters, then choose the operator of interest that shows how the target, nuclear target, interacts with external probe. Then he calculates the Lanczos algorithm with pivot, and from the Lanczos algorithm gets parameters, and again uses blue waters to construct a Lorentz integral transform method. And finally, he gets response functions. Here it's for oxygen-16. In the next research, he will be looking for response functions for neutrino experiments, because nuclear input is the second largest uncertainty in this experiment. But I would like to switch gears now and talk about some of the algorithm improvements we did last year. So we revisited construction of our basis. Even though I said that the basis construction does not represent a major problem, the truth is that for large nuclei and large Nmax spaces, it quickly becomes a bottleneck. So for instance, you can see here for silicon-28 in Nmax 6 space, the construction of basis took us 1,000 seconds, and it gets much more worse if you go to larger Nmax and heavier nuclei. So there was a fairly simple and dirty workaround, which is let's pre-compute the basis before you do your calculations. You have to pre-compute your basis, even though it's going to take hours. Store the basis on the disk, and then read it during initial setup, distribute it among collaborating processes, and so on. However, this is quite cumbersome. And another problem with this algorithm was that it was inherently sequential, due to the fact that we used the selection rules for our partial symmetries. So we come up with a new algorithm, which is much more complicated, but it gives us 2 orders of magnitude speed up. And what we really like is that for larger nuclei and larger model spaces, this speed up gets even better. And also, we designed this algorithm from the get-go to have ability to utilize multiple threads, and this picture just shows that we have a fairly good scalability. If you are interested in details, this work was recently published in International Journal of High Performance Computing Applications. And we were also working on code optimization. We did analysis of how we actually are working with the memory, and we found that during the matrix construction process, we do quite a large number of concurrent small allocations. And dynamic allocations on heap are inherently slow, and their performance depend on malloc implementation. So we try to replace the standard malloc from glibc library, and we tested all these allocators, and here are the results that we got. The best performance comes from LL-alloc. That's the red color. That's the time. But unfortunately, it expands that it increases the memory footprint by several factors, and that's really not good for our application, which is memory hungry. And so it turns out the best performance and the best memory footprint decrease is given us by tcmalloc. We were quite surprised to see that the Facebook gemalloc did quite poorly for our application. We also implemented adapted memory pooling because we are allocating a large number of small objects that have a constant size, and that is also inefficient. So the solution is memory pooling, which means that we basically allocate a large block of memory, and then we do bookkeeping by ourselves. And again, we tested multiple libraries and multiple solutions and found that the best solution is actually coming from Boost library and the Boost pool class. Another code optimization was a small buffers optimization. So in our code, we are using lots of standard template library vectors, and those vectors are doing allocations on heap. But again, in most cases, those vectors are fairly small. And so we adapted a new class that allocates, or not allocates, that uses a static buffer on a stack, which is much faster. And only in case that the size of the vector is over specific threshold, then we use dynamic allocation. And again, we adapted class from Boost library, and it works just fine for us. And this shows the overall result of our code optimization. So the blue bar is the legacy code, and this is the speed up that we have for optimized code. So it's almost factor of 2 improvement in the matrix construction. And this work was actually part of one of our students' thesis. And if you are interested in more details about his work, you can find it here online. And that takes me to the summary. I believe I addressed most of these topics during my talk. But I would like to really stress the excellent support and guidance that we got from the Blue Waters team, and it is really appreciated. So thank you.